Hello, today I'll be going over RLC circuits, which are resistor, inductor, and capacitor circuits. This is our first circuit. We can see that when the switch it opens up when time is equal to 0, or it's always open when time is greater than 0. We have our capacitor and our inductor right here, and we just have, So the steps that we want to do when solving RLC circuits is first find the initial conditions and then find alpha and omega 0. And that way we can find out which case we can do, and then when we find the case, we can just plug and chug basically. And we'll get to that later. All right, so to start out, we have time is less than 0. So that means our switch is closed, so we have a completion of the circuit with a wire right there. And with that, we want to find two initial conditions, which is going to be VC of 0, or the voltage across the capacitor when its time is equal to 0. And then we want to find the current flowing from where the inductor would be when time is less than 0. All right, and now seeing the voltage across the capacitor is pretty easy to see. It is simply just doing voltage division on this resistor, since these two are in parallel technically. So we have 6 over 4 plus 6, because the 4 ohm resistor right here as well, times 30, and that's going to give us 18 volts. And now, since this is just one big loop, we can just do the voltage source divided by the Req, which is just 10 ohms. So this is just going to be equal to 3 amps. All right, now that we have these two initial conditions, we want to find one more initial condition that's going to be dV of 0 over dt, and we'll do that when time is greater than 0. All right, to find that, just the equation for dV of 0 dt is going to be equal to IC over C, so the current going into the capacitor. So to do that, we just need to recognize that since these are the only two currents inside this loop, IC is going to just equal to negative IL, since they're going into different directions. Okay, and now we can use that to find our final initial condition, which is going to be negative IL, which we already figured out was 3, so it's going to be negative 3 amps, over the capacitance, which is 0.02 farads. And this is going to be equal to negative 150 volts. Now it's time to find alpha and omega 0. So to do that, all you need to do is look at our handy formula sheet, and we know that alpha is going to be equal to RTH over 2L. So the equivalent, so RTH in our circuit right here is just going to be 6 plus 4 ohms, which is going to be 10 ohms. Okay? So now RTH should be equal to 10 over 2 times 0.5, which is going to be equal to 10. And the next thing we want to find is omega 0. So omega 0 is going to be equal to 1 over radical LC. So that is going to be equal to 1 over radical 0.02 times 0.05 times 0.5. So this is going to be equal to 10. Now that we know that our alpha and omega naught are both equal to 10, that means they're equal. So our alpha is equal to omega naught. That means that we are in case 2. Okay. So what that means that we just follow our formula sheet so now we know that both S1 and S2 are both just equal to 10. So with that, we can just do our general equation. So V of t, it's really the voltage across the capacitor, is going to be equal to V infinity plus A1 plus A2 t times e to the negative 10 t. Perfect. And now what we want to do is use our initial conditions that we found before and to solve for both A1 and A1 and A2. Another thing to mention is that since our circuit, when time is greater than 0, has no source in it, that means that V infinity is equal to 0, so we don't even have to have that in our equation anymore. All right. So now we just want to solve for our initial conditions. So for case 2, we're going to have V of 0 equal to V infinity, which we already know is 0 since we have source free, then is equal to A1. And then our dV of 0 over dt is going to be equal to negative alpha, so negative 10 A1 plus A2. All right, so just going by the top line, A1 is be equal to 18 volt, or just 18. So this comes from this initial condition over here. And then we're going to have negative 150 is going to be equal to negative 180 A1, or no, not A1. There's 180 plus A2. So now A2 is going to be equal to 30. And with these two initial conditions, we can now finally solve for our final equation. So to do that, we'll just plug in our A2 and A1 into our general equation, which is this. So our Vc of t is going to be equal to A1, which you know is 18, plus 30t, which is our A2, times e to the negative 10t. And that's your problem done. It's pretty simple. It's just basically just following the formula sheet and you'll probably get everything right. Just a quick thing to mention, if our problem was asking for find like I of C, it's pretty simple. We just use last chapter's formula that our IC of t is going to be equal to the derivative, or the capacitance times the derivative of V of t, Vc of t over dt. All right, so in this problem, it's just going to be equal to 0.02 times the derivative of this equation. So that I think is going to be 30 e to the negative 10t plus 18 plus 30t times e to the negative 10t times negative 10. And then you just do some math and you can find what this actually really is. That's it. Here's our second problem for RLC circuits. This problem, the end result will not be source free. And you'll see that when we get to when time is greater than 0. But for now, we're going to focus on finding the initial conditions like last problem. So just like last problem, we want to find the voltage across here and the current flowing through here. All right, and what I'm going to do is I'm going to do some source transformation over here because I don't really like this 2 amp current source in parallel with that. And I just want to make pretty much just one big loop. So I'm just going to erase that. And just using Ohm's law, we're going to have a voltage source just like that. And it's be our current source, which is 2 amps times this 4 ohms to be 8 volts. And that you don't have to do that. I just do that because that's just how I kind of like solve problems, try to make it as simple as I can. Yeah. All right. And now that we can see that since this is an open circuit right here, there'll be no current flowing over here, which is nice to see. So we want to find our V0 of t and our I0. I0 is pretty easy to see. It's just going to be 60, which is our voltage source, over our Req of this portion of the circuit, which is just 10 ohms. So we have 6 amps. And VC of 0 is sort of easy to see. You just have to see the KVL loop. So we're going to start up here and go this way. So we have the voltage across this resistor. So that's just going to be 6 times IL, which is 6. And then we're going to go down over here. There's no voltage going through this resistor because there's no current over here. Same with this resistor over here. But we have this voltage source and it's active sign convention, or we're going to the negative terminal. So we have to just do -8. So this is just going to be 28 volts. And now that we have these two initial conditions, we're going to find our circuit when time is greater than 0, and we'll find our final initial condition of dV of 0 over dt. Now it's time to solve for our final initial condition, which is going to be dV of t. So to do that, we first need to find IC. But we know that IC is going to just be equal to IL because in this circuit, they're both pointing the same way, going around this way. So finding dV of 0 over dt is just going to be simply IL, which we know is 6 amps, over 0.02. And that is going to be equal to 300 volts per second. And just a quick thing to mention, what I did is that I just kept our circuit the same from greater than 0, so we just have this voltage source in series with the resistor, I mean. So what that makes our VR over here, since VR is the voltage difference from this node to this node, but we don't have those exact nodes anymore, but we sort of do. So the real VR is going to be from here, from this point, like right here. So it's our plus, and the end of this resistor right here, that's our minus VR. So the real VR now is between the voltage source, the top of it, and then the bottom of the resistor. And that's just something for later. You don't have to worry about that now. That's just kind of for when we finally found our final equation. But yeah, just pointing that out now. 2 things before we found our alpha and our omega. So first, we want to find our VTH, or just V infinity. It's just the voltage sources that are left inside of our loop. So you can easily see that we have 60 and then this 8-volt source. But since they're going the opposite directions, we're going to have 60 minus 8, and that's just going to be equal to 52 volts. All right. And now one more thing we want to solve for is our RTH. That's pretty easy to see. That is going to just be 4 plus 4 plus 2, which is 10 ohms. Now that we have our RTH and VTH, or V infinity, we now want to solve for our alpha and omega naught. So alpha is just going to be RTH, which is our 10, over 2 times L, which is just 1. And we get that just looking at our formula sheet. It should be on there. So this is just going to be equal to 5. And now we want to solve for our omega 0. So omega 0 is simply going to be 1 over LC, which is going to be 1 over 0.02, which is going to be equal to radical 50. And that means that our alpha is less than omega. So now we are at case 3. Now case 3, our general equation is going to be Vc of t, or the voltage of the capacitor, is going to be equal to V infinity, which is 52, plus e to the negative alpha, which is negative 5, t, times b1 cosine omega d, which we haven't solved for yet, but it's pretty simple to solve for, plus b2 sine omega d t. Omega d is going to be equal to the radical of omega 0 squared, which is going to be just 50, minus alpha squared, which is going to be 25. So we can easily see that this radical reduces down to just 5. So now we can plug in omega d into our general equation. So Vc of t is going to be equal to 52 plus e to the negative 5t times cosine, I forgot the b1, b1 cosine 5t plus b2 sine 5t. And now what we want to do is use our initial conditions in order to find b1 and b2. So from our formula sheet, it says that v is 0, which we solved way back was 28, is going to be equal to v infinity, which we know is 52, plus b1. Okay. And then we want to do our second part, which is going to be the dv0 over dt, which we found was 300, is going to be equal to negative alpha b1. So that's going to be negative 5 b1 plus omega d, which is 5 b2. Now that we have our systems of equations, we can find both b1 and b2. So it's pretty easy to see that b1 is just going to be equal to negative 24. And then doing some math later, you'll find that b2 is equal to 36. And now we can use both of those in order to find our final solution for Vc of t. So Vc of t is just going to be equal to 52 plus e to the negative 5t times b1, which is negative 24 cosine of 5t, plus b2, which is 36 times sine of 5t. Volts. There is our final equation, but remember we are not done yet. We still have to find the voltage across VR, which is just this big loop over here. So the voltage across there. So to do that, VR of t is going to be equal to 8 plus IC times 4. So now what we do is solve for IC. IC is equal to this is just going to be equal to 8 plus 4 times the capacitance of our capacitor, which is 0.02, times the derivative of our VC of t. All right, so the derivative turns out to be, it's going to be times e to the negative 5t times 6 cosine 5t. Oh, no. That's the next step. It's going to be 300 cosine 5t minus 60 sine 5t. All right, so now our final VR is going to be 8 plus e to the negative 5t times 24 cosine 5t minus 4.8 sine 5t. And this is all equal to VR of t.